Okay, here's another problem. This is area in polar coordinates. There's our area formula. And this one says, find the area of the region common to r equals 2 and r equals 4 sine theta. So again, graphing calculator could help. I happen to know these graphs. These are fairly basic graphs. Nobody's giving you anything crazy. Usually, it says find the area. I think on some of my tests and assignments and quizzes or whatever, I ask you to sketch the region. I want to see the region sketched. I want to see what we're talking about. Of course, in order to figure it out, I need to see what I'm talking about. R equals 2 is a circle centered at the origin, radius 2. R equals 2 is a circle centered at the origin, radius 2. R equals 4 sine theta is a circle sitting right here on the x-axis, and it's sitting here, and it's got a radius of 2. It has a diameter of 4, and it goes out here to 4, but it's centered at 2. So it's cool. They're the same size circle. That's not the best picture, but they're the same size circles sitting there. So what do I want? The region common. I want the area of the region common to both. So you got to learn what this phrasing means. I think that's obvious. Common to both is what we call the intersection of those two overlapping circles. So I want that area. All right, you got to remember, man, there's sectors emanating from the pole. That's how we're doing this. I'm going to go from the pole, and I'm going to sweep out a sector of area. So who is the function I'm going to hit when I do that? Looks like I'm hitting this r equals 2. Okay. If I would have drawn a little better picture, you got to be careful with these pictures. I think this circle is probably a little lower looking like that. And I think I need these points of intersection, which actually are angles of intersection. And I think I need because from that angle to that angle, I think I do have sectors of area that go out and hit this circle r equals 2. But before that, I think I've got little sectors of area that go out and hit this little sliver here. So I need to be working on this little sliver, which is this function, which is this r equals 4 sine theta. So anyway, that's you got to draw big, blown up, detailed pictures to see the slivers of area that you need sometimes. So I think I've got to, first of all, I want to find these angles of intersection, these points of intersection. That's not really a skill I practiced with you, but it's kind of easy. You want to know when this r equals this r. It is. We talked about tangents at the pole. I don't need that here. I need points of intersection or angles of intersection. So when I set 2 equal to 4 sine theta, I'll divide by 4. A lot of trig. I know what that is. The angle that's 30 degrees, man. That's pi over 6 or 5 pi over 6. Those are the two places where, those are the two 30-degree angles where sine is a positive a half. And look at my picture. It's beautiful. That's a perfect 30-degree angle right there, pi over 6. And over here is 5 pi over 6. So I got some options. To set this up. I think I want to set up an integral, multiply by a half out front. That's the formula. And I want to integrate. I think I'm going to do this guy first. And the function is r equals 2. So you take your function, you square it, you integrate with respect to theta, and you go from pi over 6 to 5 pi over 6. Hey, anybody, how about this? Can we just work over here on this half, and then we'll double the answer? So I'm going to go from pi over 6 to pi over 2. I'm changing my mind already. Pi over 6 to pi over 2, and I'm going to double my answer. So that gets me all this stuff. That gets me all this. I hope you're with me. But I need that sliver, and I need that sliver. And guess what? They're the same size sliver. We'll do one sliver, and we'll double it. So I need to also do that. Here we go. 1/2. That's part of the formula. 1/2. I need, my little sector's going to go out, and it's going to hit this little sliver, which is this function, r equals 4 sine theta. I got to square it. And then I just need the bounds. I mean, usually the bounds are kind of the tricky part. For this little sliver, I think I'll go from 0 to pi over 6. From 0 to pi over 6. And remember, we said we would double it. Let's double it. That'll get us this other little sliver right here. So we'll double that. It's cool to double it when it has a half out front. That's nice. All right, that's what I got to do. I mean, that's setting up the integral. I'm going to give you some problems where I say set up the integration and draw a picture and set up the integration. And when you have to set it up, you can stop. You don't have to do it. If I say find the area, then you should do it. What did this say? Oh, shit. It said find the area. All right, we can do it. I ain't scared. I need a little room. Need a little room here. Here I go. I'm going to work on this. That's a 4. And when you integrate with respect to theta, you get 4 theta. I just moved way up here. I get a 4 theta, and I'm going to evaluate it right there. That's a 1 out front. These canceled. I'm going to evaluate it from pi over 6 to pi over 2. Evaluate it from pi over 6 to pi over 2. That means you plug in pi over 2. That's 4 times pi over 2 minus 4 times pi over 6. That's a 2 pi minus a 2 pi over 3. That's a 4 pi over 3. That's what that is. That was just that's not the final answer. That's just that answer. That was easy. Let's integrate this. This is 16 sine squared theta. Hang on. That's a 16 sine squared theta. In order to integrate it, I need the half angle formula. The 16 is going to pop out front. There's a 1 out front. So hang on, the 16 comes out front. The sine squared, how do you do sine squared? It's 1 minus the cosine of 2 theta over 2. Or 1/2, that's how I did it last time. Sine squared is 1/2, 1 minus cosine double the angle. All right, hang on. That's not the integral. That's just the half angle formula. I'm going to pull the 1/2 out front. That's an 8. And I'm going to try to go ahead and integrate this with respect to theta. Here we go. I'm integrating a 1. That's a theta. I'm integrating a cos 2 theta. I think it's a sine 2 theta. I think it spits out a little 1/2. I'm doing this from 0 to pi over 6. 0 to pi over 6. Here I go. There's an 8. I plug in the pi over 6. I plug in the pi over 6. I get the sine of a doubled pi over 6. 2 pi over 6 is pi over 3, 60 degrees. What's the sine of 60 degrees? Everybody knows. It's the square root of 3 over 2. That's awesome. Wait a minute. That was me plugging in the pi over 6. Minus the 8. Now I'm plugging in the 0. There's a 0. What's the sine of 0? Sine of 0 is 0. Good. There's a bunch of zeros. Dude, this is awesome. This is 4 pi over 3 right here. This, when I distribute the 8, that's a 4 pi over 3. When I distribute the 8 over there, that is a negative 2 square roots of 3. Did I do that right? I think I did that right. And so here's the answer. 8 pi over 3 minus 2 square roots of 3. I like my exact answers. You do this exact mathematics. You could also, in addition to that, give me a decimal if you felt like it. But that was a beautiful little problem. That was cool. I'm not going to do another problem, but I want to show you something. The book has this problem. This is pretty cool. They have a circle radius A. So they just have a circle radius A, R equals A. Then they have another circle radius A sitting here. So that's a lot like what we just did. We did it with a circle of radius 2. But it could be they do it for general A. Then they put another one here. Another circle of radius A there. And I can name all these for you. That's R equals 2A cos theta. This is R equals A. And this is R equals 2A sine theta. Anyway, they do it for just a general A. It'd be nice if it had a real number, but that's okay for a general radius A. And then they say, find the area of all 7 regions. Good Lord, you see what I mean? Watch this. Like there's one region. That's a cool little region. There's another region. I'll call that region 2. Here's something out here. All that is a 3. Not that. Not that little guy, just this chunk. Which also matches this chunk. Oh, my picture's a little bad, but that 3 matches that 3. This little region is kind of cool. That's region 4, and then I think it matches this region 4. So those two match. There is 7 regions here. Sorry, 1, 2, 3, 4, 5, 6, 7. Here's another one over here. All this is a 7. So when you have these 3 intersecting circles like this, you have these 7 areas, and they say find all 7. I mean, that's a 2-week problem. Not really, but a couple days. Especially when you're dealing with just an unknown A, you just got to deal with it. Your answer will have all kinds of A's, A squareds, and so forth. Anyway, I got some of these questions for you. I like I like some of these. I might do some of these. But I just wanted to preview that problem in the book. That concept, since we were sort of working on one, it's cool to throw that other circle in there and work on these little areas. Sometimes you have to, I didn't do this problem yet, sometimes you have to, your area, your sector sweeps out this area, and if you only want this area, you have to subtract that inner area. So remember, we used to do top minus bottom or left minus right when we were working in Y's and X's. But working in this polar coordinate, it's more like the outer sector minus the inner sector. So it's not up, top, or bottom, left, or right. It's outer minus inner as we sweep out sectors. So the formula would be 1/2 outer function squared minus inner function squared with respect to theta. Outer minus inner. If you don't want that area and only want that area. So I should do an example like that probably. All right, do some homework.